Susanne Ditlevsen, hailing from Copenhagen, to give us a presentation, which she said is going to be on the blackboard.
It will be.
Okay.
So when I do my simulations, I get exactly the results I want.
Please, the floor is yours.
Thank you very much. And being at this math institute, I had to do a blackboard talk because how often can you actually get that occasion? So the title was something completely different that I gave, and this is all new work, so it's not finished, and it is what it is. So I'm going to talk about how we detect early warning signals in 3 different situations where we have multidimensional models and different distributions. So just to be clear, when I talk early warning signals, I do it in a very classical setting. I talk about loss of resilience, so that's increasing variance. And the typical thing is that this goes to infinity. And then I talk about increasing autocorrelation, which goes to 1 in the classical setting. So if you have other favorite early warning signals, you can plug them in and try to do the math yourself. So the canonical example for this, just to say, when I talk about tipping, so early warning signals for tipping, it's also the very classical situation of a saddle node bifurcation, and that means that it's B bifurcation, so B tipping, sorry, and no rate tipping here. Maybe I'll mention a little bit about noise tipping, but this is the very, very classical setting. And the canonical example of that, no, before I start with that, so I have 3 questions, and I'm not sure I'm going to answer all 3 of them because it depends a little bit on the time. But my first question is, what happens to early warning signals in a higher dimensional space? So if it is, say, embedded in RD. So the saddle node bifurcation is a codimension 1 bifurcation. So we're always looking at it in 1 dimension. What happens if we are in some setting where we might not even actually observe the right direction for the saddle node bifurcation? That's my first question. The next question is multiple time scales. So say that we have this saddle node bifurcation, but the variable that is actually going through this saddle node bifurcation has some more time scales to it. And here I will talk about acceleration. So we actually have a second order differential equation. And the last question, which is quite funny, I think, I don't know if I will have time for it. It's different noise distributions. So these are my 3 questions I'm going to talk about today. So let's start with the first one. So the canonical example is, of course, the double well potential. So canonical example. Yeah. How can this institute have so little blackboard? So I'm doing it smaller and smaller because I want the
proportional to the room.
in the end, I will be like, so all be here. So the canonical example is the double well potential. More and more abbreviations in the end. Nobody will know what I'm talking about. So here we have the typical situation of this double well potential where we have some kind of forcing. Say that we are moving around here and we have this potential barrier that it has to jump to go over here, and say that is under some kind of forcing, could for example be global warming, which is lambda 0, sorry. So this is kind of the good situation. Then the forcing changes and we might get this one, the potential barrier is smaller, and say that is some lambda which is larger than the baseline level, but it is smaller than some critical level. And then we have in the moment where the right well disappears. So I guess we have more or less all seen this. So it is the typical hysteresis diagram. So we are here. Let me not be that. I will go back and erase. Okay, so we just have the hysteresis diagram, and I just want to put the basis of where we are. So here we have the forcing or the bifurcation diagram, bifurcation parameter, whatever you want to say. And this is fixed points of whatever we are looking at. So say x of t, okay? And then we have the typical hysteresis diagram where we have unstable, stable, and stable. And in this case, for those that have not worked so much with this, here we have a saddle node, and here we have a saddle node here, and here, which basically means that a stable fixed point and an unstable fixed point coalesce, and then it disappears, okay? I don't care about this one, I only care about this one up here. But just imagine that what we have here could be lambda 0, the value of lambda 0. And then if we just make this line up, you should think about this axis, the x-axis, as different worlds or different levels of global warming. So here we are in some pre-industrial level, so that would be the steady state. And then global warming is slowly pushing us this way. And then we have a stable state and a stable state and an unstable state, steady state, okay? So that exactly corresponds to this one, and this one. So this is the double well potential that I can put into the to this one. And then of course we move, and then here we have the critical level. And what we will be interested in today is when lambda is somewhere in between here. So we start somewhere and we go here, but we are not actually crossing the critical point. So when we have any model, for example, the double well potential model, with such a saddle node bifurcation, we can make a Taylor expansion. So we make a Taylor expansion to lowest order around, we do that around some fixed point, and then we do it around the critical level. So basically we do it around this point. When we do that, any model, and I don't care which one, also the saddle node, but any model will reach the normal form. So our basic model will be this model that I then will do stochastic also. So it will be minus xt squared plus lambda dt plus, okay, let me just, before I put the plus here, of course there's some scaling that is missing here, and some placement, etc. But this is the normal form. And when we look at the critical level, we are trying to find fixed points, so zeros of this. It's quite clear that we only have zeros if lambda is negative. And it's exactly, and then the fixed point will be plus minus the square root of the absolute value of lambda. And the critical value in this case is 0. So that just means that I have moved it and normalized it, etc. But this is the normal form. And then we also, of course, want to look at it stochastically. So we have a stochastic part here, and we usually just make additive noise. And there's, of course, a reason why I made a little hole here, because maybe I want to put something there later on. It depends on whether I get to this point. Okay, so now say that this is actually our one-dimensional saddle node bifurcation model, and we want to infer different things. We want to infer early warning signals. The first thing we can do, yeah, just to say, I say Taylor expansion to lowest order. And to lowest order, of course, here means that if I don't put lowest order, but say order 1, I would have no x left. There's no linear part here. So to the lowest order, the normal form has x squared. Now, in order to...
Sorry, it's a technical question. So if you normalize the deterministic part somehow, you also change the noise in some sense, right? So
we don't care. This is conceptual. Okay. So if I have to fit the data, and I do, then we have to look at this. But this is conceptual, so don't worry about that. Now I want to understand what's going on, and this is just to give. I'm still on the basics. It's just to give these two things, so we remember why is it that we see these early warning signal of increasing variance and increasing autocorrelation. So what we will do is do a Taylor expansion of this guy, but not around the critical level, but for some lambda here in between, some lambda in between here, okay? But around the fixed point. So the fixed point is changing. It is changing down here, but we can do this Taylor expansion. And what it gives is that this is more or less equal to some rate function or restoring rate xt minus some mean that of course depends on where we are in our how close we are to the tipping point. So here we are not too close to the tipping point. We are not allowed to be. So I should have made a little hole there too. It did not come. Okay, so this is the linear model that we're looking at, and that linear model is also what is called an Ornstein-Uhlenbeck process. It's a Gaussian process, and we know mean and variance. So we have an Ornstein-Uhlenbeck process, and it has mean. That's the mu of lambda, and if you do the Taylor expansion, you see that it is just the square root of the absolute value of lambda, which is negative. Remember, we always, this is 0 now, so we always in this model here. And then we have that the variance of x of t equals sigma squared over 2 times alpha, which, okay, just believe me, that is equal, alpha is equal 2 times the square root. So here we have, so that's why I put a 4 here, and then we have again the square root of this guy. And then we have the autocorrelation, and I put a little delta here just to say that we look at some time interval. I don't care which one, but we just look at a time interval of x of t, and that is exponential to minus the lambda delta. So it's minus to 2 square root lambda. So the point here is that, look at this, and remember that the critical level is lambda c, so it is 0. So when lambda goes to 0, this one explodes. So this one goes to infinity, and when this guy, this guy goes to 0, we have the exponential to 0, so this one goes to 1. So that is the completely classical setting of why we see these early warning signals. Should also be clear that this approximation that we use in order to understand it are only valid if we are not too close to the tipping point. But we are away. We are not there yet. So let's take question 1. What happens if, say, I have some observation, I have a time series, and I believe that this time series is actually a time series of my x, okay? But we also know that when we have tipping points, we are typically in some very complex system of high dimension. Let's just say we are in RD. Hello, haven't seen you. You just came. And hello, Peter. You also saw you, even though I'm not wearing glasses. Okay, so we believe that when we have this time series, we are actually observing X. But now say that we don't really know what we're observing. We are observing some set, and we hope that set is X. But maybe it's not. So now what I will do is in my d-dimensional space, I can decide the coordinate system. And what I will do is I put one coordinate and I call it X in the direction of my saddle node bifurcation. Okay? I can just squeeze around my coordinate system. So this is X. Okay? Now I observe set in some direction in space. And I do that in this d-dimensional space. But I only observe one coordinate. Now this d-dimensional space, I can take the plane that is being created by x of t and the direction I'm looking at, set of t. I don't know the direction, but say I'm looking in some direction. And then I can find the orthogonal complement to x in that two-dimensional space. And I call it y. Okay? So that y is orthogonal to x. And it is some linear combination of d minus 1 other coordinates. And then say I observe in this direction. So this is what I observe. And what I observe is at some angle, okay? Some angle to x. I don't know that angle. And when I do my analysis, I usually just pretend set is x. So what I want to figure out here is what does it actually mean that I think I observe x, but I actually observe set. Okay, so what we observe is actually, so let's say that I have some value x here, and then we can do something like this. And what I actually observe is this one. I call it x tilde. And here what I actually observe is y tilde, and here is the true y. Say something like that. So what I observe is set of t equals cosine to my x plus sinus to my y. Okay. I forgot to put up the model, so let me just do that. I can do it. I'll do it here because then I don't use space on it. Okay. So we are in this independent setting, and I can place my coordinate system where I want to. So I have this as my x, it's still there, but then I have my dy of t, which I assume there's no tipping in it. So that is just minus gamma y of t dt plus, let's say, tau dwt, and these are two different ones, okay, x and y. So I have these two independent components. Usually, of course, they will not be independent, but now I have placed my coordinate system such that they are independent. And it's just to look what will happen. Now this one has, just like up here, so the variance of y will be tau squared over 2 times gamma, and the autocorrelation will be the same. Well, okay, it has another constant. Autocorrelation of y will be 1 minus gamma delta. Okay, so I will need these guys. Okay, so what I will do is look at the variance of set of t. Since they're independent, it will just be the sum of the two. So it will just be cosine squared, the variant of x of t, plus sinus theta squared, the variance of y of t. Okay, and now I just cheat in order to, I don't cheat, I just define some new, I don't want to drag around my cosine and my sine, so I just define, I define this is the sigma squared of my x, and I just define that to be cosine squared sigma x, and in the same way, sinus square theta tau square will be this guy. When there's such a small blackboard, order is very, very difficult. So that will be equal to, because of this redefinition, my variance will be sigma squared tilde over 4 square, oh, it should be the other way around. It will just be the sum of the two, these two guys, okay? So look at it. This is a constant. Y is not changing, stationary process. This one goes to infinity. So it also goes to infinity when lambda goes towards, let me write lambda critical just to remember what we are talking about. I could also write 0. Okay, so we see that the early warning signals are actually still preserved, except for one case. For anyone who knows their high school math, can you see in which case we cannot see it? Or you don't remember your high school math? Yes?
Yeah, so it's very likely that theta will be close to pi over 2 in high dimension. It's also, so you have not rescaled gamma at the same time as real rescaled time for x.
This is just conceptual. You can let's say I already rescaled it.
Yeah, but the point is that when you get the normal form, you have to rescale time. So here you have chosen the time scale for the instability. So then when you rescale it,
I've rescaled it now. Okay. I really don't want to talk about for real systems in that sense. So just imagine that I've rescaled it. It might be that it becomes something specific. The only thing here important is that here is a constant. This is a constant. And if you have rescaled it, it's another constant. And when we go to the limit, we always have the limit of lambda going to 0, and then we don't care about exactly what that constant is. It will be, that's correct, it will be very, very important once we go to real systems. And when we are trying to figure out, because it should also be quite clear that if this goes to 0, this one explodes. And at some point, this will be much larger than this point, than this one, and then this one doesn't matter. Which means that if we are close to the tipping point, if we are close enough to the tipping point, it matters absolutely nothing that we're embedded in some space and we're not looking in the right direction, except for if, of course, we are observing in the y direction. So if the angle is pi half, okay? So, but I would also say that you should know very little about the application you're looking at if you're looking orthogonal to what you're interested in. So I don't think that is a real danger, but of course you might have a very high dimensional system and things get more complicated. So let's say I'm a simple person, D is not too big, but it is interesting to look at it in a higher dimension, okay? So I agree on that. Okay, so this is the first thing, but there are much more to say about this. Let's look at the autocorrelation. So the autocorrelation of t will just be the autocorrelation of x plus the autocorrelation of y divided by the variance of z. Okay, so what we in the end get is times okay, let me just write it like this: variance of x divided by variance of x plus variance of yt plus, and then we have the autocorrelation of y. Oh, sorry, times variance of y divided by this. So this is just a number between 0 and 1. But what we can see again is that, okay, let me write it. Well, I'm a little too fast. Variance of y, variance of x of t, plus variance of y of t. This one is a constant. This one goes to infinity and this one goes to infinity, which means that this guy goes to 1. Okay? And this guy goes to 1. We already saw that. So this guy goes to 1. This one, a constant divided by something that goes to infinity, so this one goes to 0. This one is a constant, so this one goes to 0, goes to 1. So we still have the same early warning signals, even though we are observing here. And then I made a mistake in my notes, and I discovered that in the airplane. So I did some hopefully correct, this is really new, so hopefully correct calculations that I think is important. So let's just take this away. We don't care about this. Okay, we don't care about this. We can remember, okay? So now the next question comes. Say, now I have seen that the early warning signals are still there. Doesn't matter. Of course, the proportion, depending on where we are, the proportion of how big these are compared to one another. And if we are very far away, if the angle is very close to pi half, this will be big and this will be very small, but they're still constants. And it just means that where this one takes over might take longer time if we don't observe in the right direction. But my point, the question I now ask is the following. Say we are in this situation, but we think erroneously that we observe x of t. So we go in the direction of x of t, okay? What happens with our conclusions? So the thing is the following. Say we want to estimate the time it takes from lambda 0, and then the time it takes when it is half the value, okay? Or some proportion q. So imagine you are here, and the critical value is here, and you're moving towards that. And we want to know how far are we. So say we want to determine the t, this is negative, so I just put absolute values around. The t such that this is equal to some proportion q, where q is some number between 0 and 1. Okay? So we just want to see, of course, if we are in a stationary system and we are not approaching the tipping point, then of course there's no solution to this equation. But now let's say we assume that it is moving linearly, the lambda, towards 0, and we want to calculate this. Then we have the following. Lambda t equals let me just write this. Okay, this is just pure algebra. You remember that the variance was over here, and then we divided by the square root, and this is where the square root, now there's no square root over here, so there's a square. This is how it truly is. But the thing is, we think, we think we see this, but what we actually see, what we actually use, 4 times the variance of z of t squared. And now I haven't defined that one, and I haven't calculated either, but it is some constant we would estimate. It is not a constant, so the model is misspecified. But if we plug it into our system, we will get some x there. So there will be some a little hat. So it's something we estimate. That means that since we are trying to solve this, what we are trying to find is 1 over the variance of set 0 squared should be equal to q 1 over variance set of t squared. And we're trying to find that set that fulfills this. Okay, I'm not going to do the calculations. They are not difficult, but they are a little messy. But what we get is that lambda t equals q times lambda 0, for that t we find, times some function of lambda t divided by some function of lambda 0. Okay, this function is just these variances that I deleted before. Okay, that's just a question of the variances. Just 1 second. This function f is an increasing function with this lambda. So this will be smaller than 1. Okay, this is the conclusion, and let me pack it out. So we believe we see this, but what we actually see is q times a number that is smaller than 1. That means that the t we are estimating for, we have to go from here to there, and we believe we are here, but it actually will be here. Was that the right way? Here, we are here. We are closer to the tipping point. So what we will do is underestimate the time, overestimate. T will be too large. What we will do is doing a conservative estimate. We think we are further away from the tipping point than what we really are.
You mean closer?
No, further away. So when we are contaminated by these y's, and we pretend or we believe that we are observing x directly, this contamination will do that we are more prone to false negatives than false positives. Okay? We say the t we estimate, we believe we only moved q, but let's say 1/2. Let's say that this is, where did I put it? I don't know where I put it. The f, here, sorry. But what we actually, it was, let's say this is 1/2, was 1/4. So we are much closer to the tipping point than we think. We think we only moved half the way, but we actually moved 3/4 of the way. So we get conservative estimates. We underestimate the risk of tipping. Okay. That was the first conclusion. And I probably already used most of my time. No, I still have 20 minutes or something like that. Yeah. There was the first question. I still have 2 questions, but if you have some questions here, maybe, yeah.
So does the variance c in the denominator there mean that the nature of the underestimate is less extreme as you approach the tipping point?
It means, so we think we found that, say q is 1/2. We want to know when we go from baseline and we are half the way towards the tipping point. If we estimate that, we estimate the time it takes, say 10 years. Yeah. That 10 years, we will actually be closer to the tipping point. Not half, but even closer.
And then is it more, because d inherits critical slowing down from x or no? I'm trying to figure out if that 1 over variance is expanding as you approach the tipping point.
Yes, it is.
Yeah, okay. So the extent of your misestimate is getting worse.
I mean, once you are very close to the tipping point, you cannot do anything, but it doesn't matter. Okay. But just because everything breaks down, every approximation. But just say that, okay, we are still such that the approximation works, but we are far past that constant of y. We don't care. The contamination from y is very small. Yeah. But when we are far away from the tipping point and there's a long way, the contamination from y will matter, and that will underestimate the risk of tipping. Yeah.
So would you see this in that if you're assuming that lambda is varying linearly in time, this would make it look as though it's not from your estimates?
Probably. Yeah. Probably there would be some nonlinear thing you would believe. If you look at it and still believe that you're watching x, you would probably get some nonlinear function estimate of that. Yeah?
It's just a notation thing. Lambda naught is supposed to be lambda c. This is the bifurcation point, right?
Where?
In the total word, lambda t equals
last.
q lambda
bottom.
Oh,
naught.
it's correct.
No, that's correct. So this is baseline. So we are here. Here's the tipping. Danger. I don't know how to make an. Okay, I'm trying to make a death over here. Okay, tipping. Lambda c, and this is baseline. And then we have some lambda, and we want to estimate when we are here. We want to estimate the time it takes from going from here to here. And that is under linear lambda. Exactly, yeah. And if it's not linear, and if we look at it wrongly, we would probably estimate it's not linear, even if it is. Yes, one of you? Yeah.
So in practice, you will observe many Ys. Maybe you will not observe that, but you will observe many things.
Yeah, this is under assumption that you have one time series and you're using only one time series. Okay, so under the assumption that you only have one time series to watch.
If you have a multi-dimensional system, then what you observe is not just single scalar variable, but you will observe many of them. So I guess you can apply your reasoning to all of these variables.
Yeah.
Maybe there is one which is better than the others. I mean, maybe you can learn something from the fact that you have several observations.
That's a very good observation. I think yes. So say you have dimension 10, and you don't exactly know where x is. You could probably use those 10 to get more informed about the direction of x by using these results. If you believe in the model, if you believe in the tipping, yeah, I think so. You're right. You also had a question.
Yeah, no, just a clarification on the protocol here. Like we're changing the lambda linearly in time, but when you write those two equations at the top, we're kind of assuming that at each point in time, the system has relaxed to the stationary state, which is the Gaussian process. So it's infinitely long in a way. Like I don't know how to explain it, but
Yeah, I know exactly what you mean. Here I am pretending that at time t there is some variance, but of course we should estimate that variance, and that estimate of the variance would need a kind of a stationary window. Here I'm just bypassing that, pretending that at time t with a one measurement I would be able to estimate it. So this is purely theoretical in that sense, and one would have to think about what happens when you actually have to have real estimates. And then basically what you need is that lambda is moving slowly. Okay, I have 15 minutes left, and I have two problems, and one is quite technical, so I don't take that, and I take the last one instead, because I think it's easier for, yeah, it always happens to me, this. Yes, so okay. Very intriguing. You don't get that. Okay, so let's go back. Let's go back to because it will be too technical on the board, maybe if we don't have time. So this is much simpler in a certain sense, even though I'm just claiming a lot of stuff. So I will look at the effect of noise. Unless were there more questions to the previous, maybe in a little while. Okay, so we are here. So this is the model we are looking at, and usually we are doing all our assumptions on the fact that this is additive noise, so we just have a constant here, but say it is a function of x. And I will analyze it exactly in the regime where I'm far away, sufficiently far away from the tipping point, such that locally the Ornstein-Uhlenbeck, no, not the Ornstein-Uhlenbeck, sorry, the linear process is enough. And just to recall, now I just write this up. That is 2 times the square root of lambda, and mu of lambda is just the square root of the absolute value of lambda. Okay. Now it turns out, if I, as the sigma, takes such a function, x equals square root, I'm not gonna have, I cannot do all of it, but let's just say that I have the square root of a second order polynomial. Okay? I have a square root of a second order polynomial, so I just have ABC. ABC of structural parameters is not something that should be estimated because it depends on what model you have. This class of models, the Ornstein, not the Ornstein-Uhlenbeck, the linear with one of these is called a Pearson diffusion. Okay? It's called a Pearson diffusion because you can get a stationary distribution of all these, the entire Pearson system of distributions. So basically, this is determined by, we need something positive here. And if you think about the additive noise, it means A equals 0. Oh, sorry, there should be the square here, of course. A equals 0, B equals 0, and you just have a constant. Okay? It would just be a 1. So C would be 1, and you have the Ornstein-Uhlenbeck. Then you can actually get invariant distributions that are the gamma distribution, the skewed T distribution, the F distribution, the beta distribution, the inverse gamma distribution, all these just by choosing these. There are 6 main classes. Now, if I look at this one, then I'll just go through that. So say this is, if this is just a constant, we have a Gaussian process. And everything is nice and Gaussian. Probably when we observe our process, this guy here, we can often expect heavy tails. Okay? So say that we actually did all this wrongly when we did our Gaussian process, but actually had something with heavy tails. Okay? So we actually will look at the case where our the stationary distribution of the linear process is a skewed T distribution with some degrees of freedom. Okay, so if we do that, we will have, I have to look at my paper in order not to write this wrong, square root of 1 plus x squared. Okay, so this is just the form, and it can be shown that the stationary distribution of a fixed lambda, okay, so we don't vary anything yet, we just have a linear one, and then this one, the stationary distribution will be a skewed T distribution. And it has heavy tails. It is skewed since, let's say, the stationary point, which is just the mu over there, this one I put here, is not 0. That's what makes it skewed. We don't care about skewness for now. But what we do care about is that this T distribution, if you remember your statistics classes, the T distribution is...
I didn't get what you said. Do you use mu equal to 0 here or not?
Mu is this one. So it's only 0 in the tipping point. And in all cases, so say that we would just add a constant because we are somewhere. We could do that, but it will not be constant. It will move.
So what do you mean when you say x star is not 0?
I mean that mu lambda different from 0 for all lambda smaller than 0. So, and then a T distribution has degrees of freedom, if you remember. When the degrees of freedom converges to infinity, this converges to a normal distribution. But it has degrees of freedom, which we normally write like nu, and that is equal to 1 plus 2 alpha, so the restoring rate, that's the restoring rate, divided by sigma squared. Okay? So that is the degrees of freedom. If the degrees of freedom are 1 in a t-distribution, so if this is not here, you have a Cauchy distribution. No mean, no variance. Okay? This will never become exactly 0, because then we are at the tipping. But alpha goes to 0, and it means that when we are in the baseline situation, this will be a big number, we have lots of moments. But the t-distribution only have moments up to this, just under. So it doesn't have moments of 1 plus of the degrees of freedom. Okay? We never get exactly to the Cauchy, but we get to all others. And what should be clear is that when we start in baseline, everything is fine. And then we go towards the tipping point, and this process becomes wilder and wilder with less and less moments. And at some point, it will no longer have variance. In fact, when alpha of lambda equals 1/2 sigma squared, okay, so 1/2 sigma squared, this says 2, no variance. And that is actually where the variance explodes. So let me just do that. Let me write that. Yeah.
The moments, it means somehow expectations of x, no?
Yeah, it means that it will not integrate when you
Yeah,
take.
but I mean, you made the assumption that x is somehow near to mu to make your expansion of the model.
Yes, but
So somehow that, I mean, you killed all the stabilizing terms which you had in the model, which may rein you in.
Yeah, but if you are far away from the tipping point, you will be. You will be around that point. So this approximation is very good as long as you are far away from the tipping point. And then, of course,
Sorry? X is small. No, x must be small as well.
no, but it has a distribution around that. So the mean is still the mean is the same. So it still has that mean, and that has actually all the Pearson diffusions. So just forget about that it says a lambda here. All the Pearson diffusions has mean mu. It has the same rate. It has the same autocorrelation, but they have different variances. And the variance comes from this guy. So it has wilder behavior, but it will still behave very much like this process if you're far away from the tipping. But it will probably be more sensitive to how close you are to the tipping. So you should probably be even further away for this approximation specifically to hold. So when we look at this, there's no variance. It actually means that to the 4th, okay, if lambda is not yet tipped, but between these, it will have no variance. And actually what you see, so let me write the variance. The variance of x of t equal, the stationary variance, there's of course a conditional variance for when you observe from one point to the next. But here we look at the stationary variance in the same way as we did with the Gaussian process. That will be sigma squared divided by 4. Notice that this is the variance of the Ornstein-Uhlenbeck, but I'm not finished. I actually multiply here by 1 plus mu squared. So that will be the absolute value of lambda. We don't really care about that. That goes. It just means that in the beginning it will have larger variance, but this will disappear. But down here we have minus sigma squared. So what happens is actually the following happens. And I think it's quite interesting. So here you have lambda. Here you have the variance of x of t. Here you have the critical value, 0. And say I should stop in a second. Yes. Let's say here that is baseline, lambda 0. Okay? Now say I start the process. I have two processes, one Uhlenbeck and one this t-distribution. And I just force them to have the same variance at lambda 0 as baseline. That just means that I have to adapt the sigma for the t-distribution. Now I draw what happens in the Uhlenbeck case. I have this variance, and then it explodes. Okay? So that is the loss of resilience that I have. Now what happens with the t-distribution is here I have minus 1 over 16 sigma to the 4th, coming actually from here. What happens, so I have to do another one here, is actually, okay, we don't care. I want another color. I want another color. Here. It's actually below the Uhlenbeck, and then suddenly, whoa, and it explodes here. So it means that in the beginning, you see a smaller variance, and then they cross, and you have explosion before the tipping point. I just, okay. I'm actually finished. I just want to say something, and it's just in honor of Alan. Because this one, I remember Alan giving a talk where he said, that when you are looking at tipping points, and when you look at these complex system, you should have bounded noise. You remember?
Yeah.
You should have bounded noise. Okay, I can get bounded noise here. I can get bounded noise if I do sigma squared to be this one, and then I do, okay, I do apologize if I don't write it exactly correctly. So what I have here is x minus its mean, so I have a 0 here, and then I say, let's say b1 plus, and the same x minus, okay, now this is too, sorry if you cannot, okay. What it says is, if I have noise that is bounded between B1 and B2, around where I am, I have better distributed noise, and I can calculate everything. I still get, what happens with that one is I don't get explosion of variance. I get, when I get closer to the tipping point, the process stops being well defined. Because the mean has to be, it has to be larger. The mean and 1 minus the mean, or b plus 1 plus b1 plus b2 minus the mean, has to be larger than the variance, and the variance explodes. At some point, it stops being defined.
And what's the meaning of dWt for your bounded noise? At the first equation at the top?
Yeah, but this is still a Wiener process. It's a Wiener process. You have, it's called a Jacobi diffusion. Jacobi diffusion is a diffusion that lives, and it's also used, it's also the Fisher-Wright diffusion. That means it's a diffusion that lives on an bounded interval, and it will never hit the boundaries. So that's something you typically use when you have ratios. So that's for genes, so how many genes and stuff like that. So you can have a bounded diffusion. There are just restrictions for how big sigma will be, but it's still, it's because when you go close to B1 or close to B2, the noise is being gone to 0. Thank you.
Thank you. And yes, so the floor is open for questions or comments. Remember having discussion on bounded noise with Jeroen on the text. surprise in the matter. Please, Ilya, Freddy, and Ilya.
Okay, so I just wonder. So mean values, variances, so it's nice objects, but they are integrated objects. So in fact, what you have one sample. So this means you have a sample. So what you can do, you can calculate empirical mean, empirical variance, and they will be perfectly defined and finite. They will not explode. So how does it relate to?
Yes, I have thought a lot about that, and I completely agree. Even talking about measuring variance and autocorrelation in a non-stationary process is bollocks. Okay, so you cannot do that, except if the non-stationarity is so slow that you can make a window where it makes sense. So we have that problem. My solution to that problem is to doing proper statistical methods where you estimate directly on the process, not doing anything about windows. So this is mainly to understand theoretically what is going on with the models. Once you do statistics, of course you can still have early warning signals, and basically it would be nice theoretically to understand, because you might have no idea about where your model comes from, or is it towards tipping, and then the best thing you can do is doing running windows and then see if the variance increases. So it would be good to understand, does that happen in other models, and what if it comes from, and what if. But more proper statistical methods for stochastic processes.
And I have a very good
Yes, thanks. This was very, very interesting. So someone already asked the question, but in the real world for the A-mark, for instance, lambda will depend on time. So when it will not be fixed, as you have assumed.
Yep.
So at the point there will be a crossover.
Yeah.
After which the fact that lambda depends on time will become critical.
I'm very happy you mentioned the AMOC, because we actually employed both the Gaussian and the t-distribution on the same data set. What we get from the t-distribution is that the b-tipping, so the bifurcation tipping, happens later, but if you add to that the risk of noise-induced tipping, you will have the same risk of tipping in this century. Simply because when you have a t-distributed noise, it has large excursions and it will cross. So we actually we're just about to submit it. So in that paper we have the t-diffusion and that. Then we also do, I don't say I necessarily believe it, but we also do a model control where we do the AIC criteria to choose among the two models. Is it Gaussian or is it t-distributed? And it's the Gaussian that comes out as the best fit. But these are statistics, so yeah.
Yes. Yes, please.
Thank you. I have noticed that we firstly eliminate in the theta, and then by the lambda reaching to 0, then we can get the early warning signals and then the Gaussian noise. But I was wondering, if we move forward to the loving noise, I think maybe we could still eliminating the theta, but for the lambda maybe have some changes. And you mentioned the MOC model. Maybe we could separate this model to like about 3 types of models. For the clean models, that this method could still used under the living noise, and not that clean model maybe make some modification, and totally cannot be used under the living noise.
First of all, I've never tried anything with Levy noise, but my guess is that we would get some of the same results, because I think this t-distributed noise is a good, let's say, indicator of what we would see in more extreme noise types. And I'm not sure about.
Or because of this is the tipping point, and maybe loving noise being caused about the n-tipping points, because about more of noise.
Yes, yeah. It would be interesting to look at. Very interesting to look at, yeah.
Yeah, a comment on this. I think Larissa will talk about noise, yes, noise
But not
distribution.
GV, just with
Yeah.
what we already submitted. But
Which-
yeah, we have some results for GV.
And I think it's closely correlated to the theory of shock noise where he has been working on it, because the heavy noise is like a big kick.
Yeah.
Of the systems. So here, sorry.
Yes, but I mean, if you're in, I mean, I understand that maybe you get a problem for the bounded noise. No? You get an existence problem because there's not Lipschitz at the boundary in the. So if you make it Lipschitz, just put squares.
Yeah, but then you get another distribution. So it depends on what distribution. It's just that I have this from my toolbox, just all the Pearson diffusions with all these distributions.
It's more explicitly solvable, but I don't see the point, because in some sense, I mean, it's not surprising that if you increase the value, the variance get bigger, you see bigger fluctuations. I mean, that's in some sense.
But you might still be, for where you observe, you might still be within the interval where the process is still well defined. And then if you believe in bounded noise, you would be, if you believe in this, it's a beta distribution, and you could estimate the skewness, and you can estimate all kind of things, and that might help you to understand something about the system. The only thing is that for this, I believe that the linear approximation breaks down earlier than it does maybe for the other models. So it's just a question of for how long can you actually use these approximations. But I can also say that for the Gaussian case, if you simulate from Newton Uhlenbeck this one, or you simulate from that one, if you are just tiny away from the tipping point and you use the same realization of the noise, you cannot see the difference between the realization of the processes. They are, you really have to be close. For the other noise types, I guess a little further away you start to see the difference. It's just to say the linear approximation is really good, as long as you're not too close to the tipping point.
Last comment by
Yeah, I've got a question. Yeah, for TP, we talk about a finite time horizon. Then on the finite time, the Brownian motion is bounded. So the noise intensity is also bounded on finite interval. So what do you mean unbounded noise here?
No, I just mean the distribution is unbounded. I just mean that if it's beta distributed, it's bounded within minus B1 to B2. But if you have T distributed, it's on the whole real line. If you have Gaussian, it's on the whole real line.
Yes, I think we have to cut. It's a bit late. Okay, you want? Yeah, very short.
Just so because you triggered me with the bound.
I was joking. Next, but careful, because I could poke Sebastian, and then he goes into the zombie fire. So I'm very scared.
But it's just an example. So if you have something with bounded noise, you can have like a bounded distribution. There's a sum kind of drifts off. This is basically like your tipping point. It's like a settle node, but not really a settle node. So just the bounded region just explodes. So for that, you can show that variance could even decrease when you go to bifurcation point, and all the statistical measures don't work. The point is a bit like this variance works very well for one model. If you perturb this model into other things, it's completely unclear what this variance actually means. So we should look for things that are beyond simple things for simple models.
Yeah, I actually have a biological model where we do have decrease of variance right before it tips and then up.
Yeah, so we just need to be careful not to bring simple messages to.
But now this is under this model, and there's reason to believe this model from physical understanding. And
Okay.